Hi, my talk is about fast parallel algorithms for Euclidean minimum spanning tree and hierarchical spatial clustering. My name is Yiqiu. This is work done at MIT with Shangdi, Yan, and Julian. In this talk, we'll focus on density-based clustering, where we identify clusters such that each of them is a contiguous region of high-density points separated by low-density ones. It has many different applications listed here. We focus on the most famous density-based clustering algorithm, which is the DB-SCAN. It's invented in 1996 by et al. It has many different advantages. First of all, it doesn't require the user to specify the number of clusters beforehand. It detects arbitrarily shaped clusters, and is also robust to noise. On the right, we compare DB-SCAN with a naive version of k-means on two different datasets. For the first dataset, we see that DB-SCAN correctly identifies these two clusters that are nonlinearly separable, whereas k-means actually fails. For the second dataset, we see that DB-SCAN identifies the core part of these clusters while rejecting some of these data points as noise, but k-means give a somewhat less optimal cluster. This is a more specific example of how a DB-SCAN-like algorithm can be helpful in a real-world scenario. This is a dataset of a street map where each data point is a coordinate where people live or move. So the goal is to identify the densely populated regions on the street map. As we can see that the clouded regions are the clusters identified by the DB-SCAN-like algorithm. So we can see that these clusters are of very arbitrary shape. And in addition, these black regions, although containing data points, they are not identified as clusters because they are not dense enough to be recognized as clusters. So this is where DB-SCAN-like algorithm can be helpful. Here's the motivation of our work. I have just talked about the DB-SCAN algorithm. It is very useful, but it only returns flat clusterings. So it does not address varying densities and nested clusters in the dataset. It also has two parameters that require tuning. In 2015, Campello et al. Proposes hierarchical DB-SCAN star, which we will call HDBSCAN for short. This algorithm outputs a hierarchy that captures varying density levels. So the flat clustering that can be extracted from this hierarchy closely resembles that of DB-SCAN. So they call it DB-SCAN star. This algorithm only requires one parameter, which requires less tuning. Our works focus on parallel algorithms. So in 2020, we designed theoretically efficient and practical parallel DB-SCAN algorithms. And for this talk and this paper, we focus on parallel algorithms for HDBSCAN. This is the outline of my talk. First, I'm going to define the problem. Then I'm going to talk about parallel HDBSCAN algorithms, which mainly involve three parts: the well-separated pair decomposition, the minimum spanning tree, and the dendrogram. Lastly, I'm going to talk about experiments. So here's the problem definition of HDBSCAN. Like other hierarchical clustering problems, first we need a measure of dissimilarity between any pair of objects. So HDBSCAN, this is called the mutual reachability distance. With the mutual reachability distance, we can construct a graph which is complete and undirected, and where we add one edge between every pair of objects, weighted by the dissimilarity measure. Then with this graph, we can further compute its MST, and further from the MST, we compute the dendrogram, which is the cluster hierarchy. Let's start with the first step, which is converting the dataset into a graph. So we need to define the measure of dissimilarity. The HDBSCAN problem takes in one parameter m. So in the example that I'm going to show on the right, I use m equals 3. First, I define core distance. The core distance of a point P is defined as the distance from P to its mth nearest neighbor, including P itself. In example, I'm going to use E. So E's third nearest neighbor, including E itself, is F, from which E has a distance of square root of 5. Therefore, E has a core distance of 5. So with core distance defined, I'm going to define mutual reachability distance, which is the dissimilarity measure of the HDBSCAN problem. We use D and E as an example. D, likewise as E, has a core distance of square root of 10, and distance between D and E is 6. The mutual reachability distance between D and E is the maximum among the three numbers, which is 6 in this case. So we see that based on how this mutual reachability distance is defined, it captures both density as well as distance between two objects. This is because if an object is in a sparse region, it tends to have high core distance. And on the other hand, the distance between objects is captured in this term of the mutual reachability distance. Okay, so now we know the dissimilarity measure between any pair of objects. We can construct a graph which is complete and undirected. And after that, we can compute the MST of this graph. With the MST, we further compute a dendrogram, which is a cluster hierarchy. So now I'm going to zoom into this part, which is computing a dendrogram from MST. Specifically, I'm going to go through a serial algorithm that does this, and also why this dendrogram is so useful. So on the left, I show the MST of the mutual reachability graph that I have just talked about, and note that the edge weights here are not necessarily in scale to its Euclidean distance between its endpoints because of the core distances in our distance measure. And on the right, I show a dendrogram that we're going to construct. So a dendrogram is a tree where the leaves are the input objects, which I show on the x-axis. And on the y-axis, I show the edge weights. So the edge weights are actually just the dissimilarity measures of the graph that we construct. So to construct a dendrogram from the MST, we first sort all the edges of the MST from smaller weight to larger weight. And then we process the edges one by one. Let's look at the smallest edges of the MST, which are these two edges. We first process them and add them to the dendrogram. So we do so by connecting the leaf nodes that are associated with these edges and form a small subtree. After that, we process the next edge, which is FH. Similarly, it connects the leaf nodes with the existing subtree. We do similar things for the remaining edges, and eventually we form the entire dendrogram. And note that for each of the internal node of the dendrogram, which corresponds to an edge in the MST, its height in the dendrogram corresponds exactly to the edge weights in the MST. For example, D has a weight of 6, so node D will have an edge weight of 6 too. So now we have a dendrogram. How do we use it? Some people like to just visualize the clusters directly from this dendrogram. For example, maybe there's a cluster, and maybe here is also a cluster. On the other hand, we can also extract flat clustering from the dendrogram. We can do so by slicing the dendrogram at a certain edge weight value, for example, 4. So we do so by discarding all the nodes that is above 4 and look at the remaining subtrees, which corresponds to clusters. And correspondingly, on the MST, this is equivalent to discarding the edges with weight larger than 4 and look at the remaining connected components. And this gives us a flat cluster which resembles DBSCAN. So this is very useful because we can actually cut the dendrogram at other values and obtain different clusters. But this is also pretty expensive to compute. So this is a summary of our contributions. We designed parallel algorithms for HDBSCAN, which mainly consists of 2 parts. The first part is a parallel MST computation plus optimizations. We do this step for HDBSCAN clustering, which generalizes single linkers clustering. The MST algorithm also works for Euclidean MST. And then for the 2 clustering problems, we also design parallel dendrogram algorithm, which converts the MST into a cluster representation. So our parallel algorithm for the dendrogram, to our best knowledge, is the first efficient parallel algorithm to compute a dendrogram. We believe it's also of general interest to other hierarchical clustering problems. All of our parallel algorithms are theoretically efficient. We use the work and depth model for parallel algorithms, where we use a directed and acyclic graph to represent an algorithm. Each of the node of the graph represents an operation in the algorithm, and each of the directed edge represents a dependency. So if 2 operations do not have any dependency between them, they can be scheduled to run in parallel by a scheduler. The work of the algorithm means the total number of operations in the algorithm, and the depth of the algorithm refers to the length of the longest dependency chain. So for our parallel HDBSCAN algorithm, it does the same work as the sequential algorithm, and it also has polylogarithmic depth. And this translates directly to high parallelism in theory and high performance in practice by a suitable scheduler. They are also space efficient. Our parallel algorithms are also practical. They outperform the existing serial and parallel implementations by up to several orders of magnitude. On 48 hyper-threaded cores, they demonstrate 11 to 55 times self-relative speedup. Now I finished the first part of my talk. Next, I'm going to talk about parallel HDBSCAN algorithm. So the first part is well-separated pair decomposition. So for the sake of simplicity, for the parameter of HDBSCAN, which is m, I'm going to use m equals 1 from now on, and we include more details for higher values of m in our paper. So for well-separated pair decomposition, we use the short form WSPD. Previously, as mentioned in the definition, we need to construct a graph of quadratic number of edges, which is impractical for large data sets. The reason why we want to use this WSPD is that it generates a graph of only a linear number of edges, which is more efficient in both theory and practice. To construct the WSPD, we first need to construct a spatial tree, which we call a fair split tree. This is first proposed by Callahan and Kosaraju in 1995. So it is a binary spatial tree where each internal node is a split-in hyperplane and where each of the leaves are the points or the input objects. So we visualize the example on the right. So we have all these points on the 2D plane with a bounding box surrounding them. To construct such a tree, we first divide the space exactly in half. And then this hyperplane becomes an internal node, and its two children are the points in its left and right half respectively. And recursively and in parallel, we do the same thing for the children until every child is a leaf, meaning it only contains one point. So this is our fair split tree. So with this fair split tree, where I'm going to define well separation, I'm going to use the notion of point set and tree node interchangeably. In my example, I'm going to use node Q2 and Q6, so which contains leaf node ADBC and leaf node FGH. And I visualize the 2 point set representing them on the 2D diagram. So basically, while separation is saying, so we say that these 2 point sets are well separated if the distance between their bounding spheres is large enough with respect to the sizes of these 2 spheres. A well-separated pair decomposition is a collection of such pairs in the fair split tree that we construct. So this is a visualization of the WSPD of the dataset. It has a number of good properties. There are only a linear number of such pairs, and every unique pair of input points can be found in one and only one well-separated pair. In our paper, we proposed a parallel and practical WSPD algorithm, but due to time limitations, I'm not going to explain it here. Please refer to our paper for more details. And now I have explained the first part. We have the well-separated decomposition. The next step is to compute MST. You might be wondering, with this well-separated pair decomposition, how do we convert it into a graph? We use the bichromatic closest pair. Given a well-separated pair, we simply take the closest pair of points and add one edge between them. So in this way, we can convert each well-separated pair into an edge. So just a recap. So for naive algorithms, initially we had this quadratic number of edges graph, and now with WSPD, we only have linear number of edges due to linear number of pairs. But actually, this is still expensive in the practice. This is because this n here, when expanded, it actually looks like this. So there's a fairly large constant here, which is especially large when the dimensionality of the data set is high. On the other hand, computing BCCP is also expensive. So the first thing we need to do is to save on the BCCP computations for edges that are not part of the final MST. So for example, for this WSPD graph, we see that there's a cycle, which means this edge shouldn't belong to the MST. So we may be able to save on its BCCP computation. Before I go into the algorithm, here's some background. Kruskal's algorithm is a famous algorithm for computing MST. It takes all the edges, sort them in order of lighter to heavier weight, and then add them one by one to the MST. So if the added edge doesn't cause a cycle, it got added, and otherwise it got discarded. In 2010, Chatterjee et al. Proposed a Kruskal algorithm based on the Kruskal's algorithm to solve the Euclidean MST problem. They used a filtering technique to only process a subset of the odd edges, which is more efficient. For our work, we propose a parallel Kruskal algorithm and propose optimizations for parallelism, speed, and space. And we use this algorithm for both Euclidean MST and HDBSCAN. Now I explain the parallel GFK algorithm. Here's our notation for a well-separated pair, where on the first line, I show the 2 nodes involved in the pair, and in the second line, I show the cardinality of the pair, where it is the sum of the sizes of the 2 nodes involved in the pair. The first step of the algorithm is to order the well-separated pairs by their cardinalities, as shown here. The algorithm is ground-based, so intuitively, we first want to process the pairs with a smaller cardinality. So in round 1, we set the threshold and cardinality to be 2, and only process the 4 pairs that qualifies. We visualize their edges on this Euclidean plane, and we see that one of the edges is actually quite long. This is concerning because Kruskal's algorithm requires to process edges from shorter to longer. So this edge potentially violates the Kruskal's algorithm. So we use the remaining pairs that has not been processed to cheaply prune off this edge here to not process in round 1. And we only send the rest of the edges to the Kruskal's algorithm. In round 2, we double the cardinality threshold and look at the pairs that qualified, and note that this pair that got pruned out in the first round got processed again in this round. And we check whether they can be processed in Kruskal's algorithm in this round, and turns out they all are. So we add them to the Kruskal's algorithm and got a larger MST. And note that here's our MST here. And if we zoom in into this node Q2 and Q6 in our well-separated pair decomposition, we see that it has not been processed. But however, the points involved in this well-separated pair are already connected in our MST. And that means any edge generated by this well-separated pair will not be used by the MST algorithm anyway. So we can prune out this edge using filtering, and we don't have to compute its BCCP ever. The remaining of the algorithm is similar, so eventually we'll have a complete MST. For our parallel GFK algorithm, we make careful use of parallel primitives, and we do some tricks to make sure the algorithm only has logarithmic number of rounds, and this leads to polylogarithmic depths, and it also has quadratic work. We also design a memory optimization for the parallel GFK algorithm. Remember that at the start of the algorithm, we first have to compute this WSPD, which involves a huge number of well-separated pairs. So it can be this large in theory, and also very large in the practice. So we can avoid computing them by retrieving each of the pairs from the fair split tree directly only when necessary. So this saves memory of up to 10x and improves running time of up to 8x. We also define new definition of well separation for the HDBSCAN problem. So remember in the example that I have talked about previously, I've been using this parameter m equals to 1. This essentially makes the HDBSCAN problem to be equivalent to the Euclidean MST problem. So existing work that adapts to the cases where m is larger than 1 actually generates order of m squared times n edges for the base graph before we compute the MST. And this is actually quite expensive. For our work, we define new definition of well separation for HDBSCAN that only generates a linear number of edges. So this improves both running time and space usage in both theory and practice. I finished talking about the parallel MST algorithm. Due to time limitations, I'm only going to talk about the parallel dendrogram algorithm briefly. Previously, in the problem definition, I've talked about a serial dendrogram algorithm. Specifically, we process the MST edges one by one and add them to the dendrogram in an agglomerative fashion. So if the dendrogram is very skewed, this can easily lead to a linear dependency in the algorithm when we're trying to parallelize it. So instead, for our parallel algorithm, we use the top-down and divided conquer approach, where we incur only log n recursive levels of dependency in the parallel algorithm, which eventually leads to polylogarithmic depths. To our best of knowledge, this is the first efficient parallelization of this dendrogram algorithm, and is also of very general interest to other parallel hierarchical clustering problems. Next, I'm going to walk through some experiments. So this is our experiment setup. We test on AWS machines with 48 cores and two-way hyperthreading. It has 192 GBs of RAM. So here's a recap of the method that I have introduced and which we are going to show here. And WSPD naive is the method where we generate a linear number of edges. It's pretty expensive to compute all their BCCPs. For the parallel WSPD GFK, it only considers a subset of its WPD and uses filtering to prune out some of their BCCP computations. And for our memory optimized GFK, we call it WSPD memo GFK. It avoids materializing the WSPD altogether, and it still runs the GFK algorithm. And here are our results comparing the three methods. The two plots show here are for the two different data sets of different dimensionality and sizes. The x-axis shows the number of threads. The h here after 48 refers to hyperthreading. And for the y-axis, we show the speed up against the best serial algorithm. So in our experiments, the best serial algorithm is actually our parallel algorithm running on one thread. So the higher the line, the better the method. So as we can see here, that the red line is highest among all lines, and this corresponds to our best WSPD memo GFK method. And it is up to 17.7 times faster than the other baseline method running on all the threads. We also compared with other people's implementations in previous papers, and we outperforms all existing serial and parallel implementations by up to several orders of magnitude. On 48 hyperthreaded cores, we achieved 11 to 50 times x self-relative speedup. Here's my conclusion. So this is a recap of our contributions. We designed a parallel MST algorithm and dendrogram algorithm for HDBSCAN and Euclidean MST. We open source our code on GitHub. Here's the link. It's written in C++ with a nice Python wrapper. So you can just call our code in 2 lines of Python while enjoying high performance on multiple cores. Please also check out our full paper on arXiv. Thank you.